Compound inequalities are when we consider two inequalities at a time. And the solution that you get out of it depends on what type of inequality you have. So this top inequality is called an AND inequality. The solution to that AND inequality is what works for the first inequality, which you see here, and for the second inequality. So an AND inequality is the overlap between the two inequalities that are given. An OR inequality, such as this one in the blue box, is a solution set that works for one inequality or for the other. So instead of looking for an overlap, you're instead looking for anything that is shaded. All right, so I'm going to start with the AND inequality, and then we'll take a gander at the OR inequality. Now, this AND inequality is merged together. The word AND doesn't exist. So what we're going to do is break this into two inequalities. I have 3 is less than x plus 7. And I also have x plus 7 is less than or equal to 15. So these two inequalities share this middle piece. And so because they share that middle piece, I put it in both of my new inequalities when I write it out. So then I'm going to go ahead and solve these inequalities. The inverse operation of adding 7 is to subtract 7. And I like to write my inequalities to where the variable goes first, so I'm just giving that a little flippy flop. And I'm going to do the same thing here with the red. So I'm subtracting 7 from each side and having my variable first. All right, so when I go to make my number line, I need to have on it a -4, 0 of course, and 8. All right, now I tend to do like a little pre-graph up above it before I make my decision on what this should look like. So x is greater than or equal to -4. It has an open endpoint because it doesn't have the equal to bar. And then it's shaded to the right because these are where all the numbers are greater than -4. For x is less than or equal to -8, I get that shaded endpoint because it has the equal to bar. And less than 8 is shaded that way to the left. So on an AND inequality, what I'm looking for is where I see the red and the blue. All right. So if I start over here, this portion of the graph is not red and blue. This is only red. The overlap occurs right here. Okay, so on my solution, I'm going to go ahead and shade or put my ring here. And then I see my overlap, 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 up until we reach this other endpoint at 8. All right, that's when they stop overlapping with each other and it turns into just blue. So I'm putting this endpoint right here at 8. And then I'm shading heavily between the two. So notice that my lines do not continue past, all right? There is no shading past the endpoint. It is clearly defined. Also, my endpoints are very largely drawn, and you can tell which one is shaded and which one's hollow. It's really important to be clear and concise with your drawings as you do this. All right, this part that's up here, this part that's the coloring pre-sketch, that is not part of the answer. The answer is only this piece here written in black. All right, so let's compare that to an OR inequality. All right, so with the OR inequality, I see 2x in it. So I'm dividing by 2 because that's the inverse to the multiplication between the 2 and the x. And that gives me x is greater than 4. And here in the red, I see x plus 5. So to undo that addition of 5, I'm subtracting. And don't forget, guys, if you end up having to divide by a negative, we would have had to switch the direction of this alligator. Okay. So then I'm going to draw my number line. I need my number line to have a number 3, 0, and a 4. All right, so the -3, 0, and 4. And then I do a pre-sketch up above it so that I can understand what shape I'm going to have. The blue inequality says x is greater than 4. So that would put an endpoint at 4 with an open circle because there's no log that alligator's on. And greater than 4 shades to the right. For the red, I'm going to put my ring right at -3. And if I read that, it says x is less than -3. So it shades to the left. So when I go to choose what my solution should look like on my number line, it has to work for the blue or for the red. That's what makes it an or inequality. So anywhere that I see blue or red gets shaded. So here on the left, where that red is, that counts as blue or red. And here on the right, this part gets shaded because it counts as blue or red. And that's your generic shape. All right. So this is the most common shape for an and inequality. I call it the Q-tip. This one is the most common shape for the or inequality with the outward facing arrows. Okay. Those aren't the only possible shape for compound inequalities. So for example, say I have two inequalities. We'll do this, -3, -2, -1. So say I have two inequalities. The blue one, which sketches like that, that's x is greater than -2. And the red one, which I'm going to shade like this, which is x is greater than -3. So if this was an and inequality, remember the and only works for where they overlap. So if I look for overlap, I only see it here and here. So an and inequality would graph like this. Now let's compare that to an or inequality. So if it was an or inequality, it would be anywhere there's red or blue. Well, the farthest to the left for the red or blue is at -3, and then it shades that way. So the and inequality and the or inequality both looked very similar. It's just the and was only the overlap, and the or was everything. So they don't always form the traditional barbell or two arrows pointing out. Sometimes they overlap like this. Sometimes with or inequalities, you might have one, let me adjust this blue. You might have one that has like an endpoint that faces that way. Well, this goes forever left, this one goes forever right, and this would cause your entire number line to take over. The answer to this one, if it was an or inequality, would be shaded like this with all real numbers. So just be aware. These are the two most traditional. However, sometimes these odd special cases do arise.